Using KSP to calculate the solubility of a compound. So first of all, don't get freaked out by KSP. It's just an equilibrium constant, okay? The SP is just standing for solubility product. So for any kind of ionic compound that is sparingly soluble, so not completely soluble, so some metal component, some anion component, and that is a solid, it will dissolve into the cation, and this is simplified. The cation might not be a +1 charge, could be a +2 or a +3, depends on the cation, right? So it will separate into the cation and anion component. And again, the anion may not be a 1- anion, okay? It depends on which ion it is. So you really have to recall from Gen Chem 1 what your common ion charges are for main group elements, okay? And that is going to be an equilibrium situation. So we can write an equilibrium constant expression for it. So that's going to take the general form K and the subscript SP for solubility product. So remember, it's the concentration of the products, each raised to the power of their stoichiometric coefficient, divided by the concentration of the reactants, each raised to the power of their stoichiometric coefficient. But we have to follow heterogeneous equilibrium rules. So we can only include things which have a concentration or a partial pressure. So that means we're only going to include the cation, because that is aqueous, and the anion, because it's aqueous. Okay, so KSP expressions are actually relatively simple because the solid ionic compound is not going to appear in the KSP expression. So to tackle this kind of problem, you need to look at your ionic compound, in this case lead-2 fluoride, and you have to be able to pick out what ions it's going to break apart into. So I gave away the clue already by naming it correctly, but each fluorine is a -1 charge, so that means that lead has to be lead-2 to balance that. So it's going to break apart into lead-2 plus AQ. And what's your stoichiometry? 2 fluoride ions are going to be yielded for every 1 lead-2 fluoride unit that dissolves, okay? So just be aware of that. So then if I was to write my KSP expression for this, my KSP expression is just going to be the concentration of lead-2 plus at equilibrium times the concentration of the fluoride ion at equilibrium, but that from stoichiometry will be raised to the power of 2. So watch out for that. So you will have to look up the KSP value in your ALEKS data table for the particular ionic compound you're asked about. In this case, for lead-2 fluoride, that should be 3.30 times 10 to the power of -8. So it's a pretty small equilibrium constant that's telling us that the lead-2 fluoride is sparingly soluble. Okay, so the equilibrium does not go very far to the right. So just like we did for any other equilibrium calculations, we need to work out the concentration of lead-2 and the fluoride ion at equilibrium in terms of X, the change in concentration of one of those components. And I'm going to let X be the change in concentration of the lead-2 ion, because the stoichiometry lead-2 is a 1-to-1 ratio. So we only need to work this out for the lead-2 and for the fluoride ion. So let's go ahead and work out our ice table, being careful with stoichiometry. So initial, change, equilibrium. So before we try and dissolve any of our sparingly soluble compound, we should have 0 of each of those ions. Okay, then the change is going to be that as the lead-2 fluoride dissolves, for every 1 mole of lead-2 fluoride that dissolves, we yield 1 mole of lead-2 ions. So we'll let that be plus X. For every 1 mole of lead-2 fluoride that dissolves, we're going to yield 2 moles of fluoride ions. So be careful with the stoichiometry there. Add my initial and change down each column to get my equilibrium values in terms of X. So at equilibrium, my concentration of lead-2 plus is X, and my concentration of fluoride ions is 2X. So now I can just stuff those numbers in my KSP expression. So KSP equals X times 2X, and that will be squared, because look at our equilibrium constant expression. So KSP, I'll worry about the number later, is going to be X times 2X squared is going to be 2X times 2X. So that will be 4X squared. And then I have to times all that by X. So I get a relationship between KSP and X, and that is going to end up being 4X squared times X is going to be 4X cubed. Okay, so algebraically, I can rearrange that and make x the subject fairly simply. So x will be the cubic root of ksp over 4. This is going to be a nightmare to draw, so bear with me a second. Either that, or alternatively, ksp over 4 to the power of 1/3 is the same as the cube root, right? So I'm going to try and make this look pretty. Probably fail miserably. And that is my cube root. Can I just draw? Let's see. I'm going to try and draw a nice little 3 here. Oh, that turned out better than I thought. Okay, can I repeat that? So then that is going to be, if I substitute in my actual number for KSP, that was 3.30 times 10 to the power of -8. Divide that by 4. Be careful with your calculator and putting things in parentheses, etc. Okay, so then take the cubic root of that. The order you put this in your calculator may vary. You may have to put in more parentheses than you think. Alternatively, if you don't have a cube root button, that would be equivalent of doing 3.3 times 10 to the -8 divided by 4 and take whatever that equals and raise it to the power of 1/3. That's the same thing as taking a cube root. Anywho, I digress. I'm going to get a value for x, which is going to be the equilibrium concentration of lead 2 plus as being 0.002021 moles per liter. Now that is the same as the molar solubility. Molar solubility is in moles per liter, so it's analogous to concentration. And we've been asked for solubility, and solubility is in grams per liter. So to get to solubility, we have to find a way of converting moles per liter into grams per liter, and the conversion factor for that will be the molar mass of our ionic compound, so the molar mass of my lead 2 fluoride. So if I add that all up, molar mass of PbF2, well, lead is going to be below 207.2 grams per mole. And then we've got 2 fluorines, each of those is 19 grams per mil. So that gives me a molar mass of, the suspense is killing me, 245.2 grams per mole. To use it as a conversion factor, I strongly recommend writing it out as an equivalency. So every 1 mole of PbF2 weighs exactly 245.2 grams. And it's easy to take your molar solubility and just convert it into solubility. So 0.002021 moles per liter. So if I then take my molar mass, I want the moles to cancel out. So I'm going to put 1 mole of PbF2 on the bottom for my molar mass and 245.2 grams on the top. So let's just check that units are good. So we end up with moles cancelling out and we get units of grams per litre, which is our solubility. So drum roll, please. If I stick that on my calculator, 0.4955 grams per litre. And we are asked for 2 significant digits. So 0.4955 to 2 significant digits. That is a 5 there, so we've got to round up. So that will be 0.50 grams per litre. All right, so hopefully that is helpful for you. The main things to watch out for is stoichiometry of your equilibrium. So watch out if you don't have a one-to-one stoichiometry. Make sure you do also reflect that in your ICE table. So it appears both in the KSP expression and in the change row of your ICE table. So just be aware of that.